Okay, so I made one video about quality factors and bandpass filters, and it's pretty long, and I went off on a lot of tangents and proved some stuff. So here's one that's just the basic facts. All right, so you've got, you want to have a bandpass filter. So what does a bandpass filter do? It filters, it allows through the frequencies within a range, and it filters out the frequencies not within that range. So you have your peak frequency, which happens at omega naught, the center frequency. The magnitude there is m naught. That's called the gain factor right there. You have your two corner frequencies, omega C1 and omega C2. And your bandwidth is the distance between those. So the bandwidth is omega C2 minus omega C1. If I put those in the right order, I don't know which one is bigger and which one is smaller. C1 is smaller. Yeah, okay, so I have that right. All right, and then so omega naught is the middle of those, so it'd be omega C2 plus omega C1 divided by 2. Or you could take your bandwidth and divide it by 2 and add that to omega C1, and that would also be your omega naught. So that would be another way of getting it. And it is also true that omega naught is if it's the geometric mean, is it also the arithmetic mean? It's the square root of omega C1 times omega C2. But yeah, that is correct. Yeah. And then you see the other, it's an approximate, because it's a geometric mean and not an arithmetic mean. So this is approximate. So this is the true definition, and this is an approximate definition. Okay, so but those are not the only definitions at all. Okay, so that is a bandpass filter. So it allows in the frequencies in this range and does not allow in the frequencies on the other range. There's two types of bandpass filters. Well, there's lots of types, but two main types. You have the series, where you have RL and C in series, and you have the load in parallel with the resistor. You can also have them all three in parallel and the load in parallel with all of them. I had said in class or in the session that you had it in, I drew it like this. With a voltage source, and this is drawn with the current source. These two are identical, just with different sources, but they are the same. So this one, this would have a transfer function as with the voltage out over the voltage in. This one has voltage out over current in, so that makes it a little different. If you wanted to get the transfer function in terms of voltage, you'd have to derive it from this circuit right here. For both of them, the resonant frequency is 1 over square root of LC. Yay, that's what it always is for RLC, or it seems to be. Now, the bandwidth for the series is R over L, which is the reciprocal of the time constant for an RL circuit, so you might remember it that way. And the bandwidth for the parallel is 1 over RC. Now the quality factor tells you something about how specific your filter is. So it has to do with like how, the range of your frequencies. So the quality factor is your center frequency divided by your bandwidth, and so the smaller your bandwidth, the bigger your quality factor. And so you see omega naught over B in the series, that is omega naught L over R, And in the parallel, it's r over omega naught L. You might think, well, why is it not omega naught over 1 over RC? It is. Those end up being the same. That was one of the tangents I took on the other video. So, but these are the quality factors that you need for these two types of bandpass filters. And then these are the formulas that you would have to find your center, your half power frequencies. That's another name for the omega C1 and omega C2. So you could use these to solve a design question. So if you had to design a bandpass filter with, you know, a Q equal of something, and you know, you add some other things, you can just use these formulas to fill them out. And I think that will be it for this video. If you want more, you can watch the other video. Let me see if there's anything else. No, that's it. All right.